All right, here's a problem where we're trying to find an equilibrium constant for this reaction in yellow, and the information we're given is we're given these three reactions with their values of K. We have to manipulate the three reactions to get them to match the one we're trying to find. Then we'll manipulate the Ks appropriately and multiply them all together. Very similar to a Hess's Law problem that we did back in Chem 1, except for the Ks behave differently than the delta H's did. So I have reactions 1, 2, and 3. I'm going to go through and label them that way, and this becomes a matching game. I have CH4 that I'm trying to find in my given reaction, my desired reaction, and as I look down to reactions 1, 2, and 3, I find CH4 right there, and that's the only place I find CH4. If I found it in more than one place, I would skip it and try something else. I'm just trying to match them at this point because that's what I have to do to figure out how to manipulate them. If I find it in more than one place, it becomes more difficult to match, so I'm going to skip it and try to find something easier to match. So reaction number 1, in order to make it match, it is in the correct side. It's in the reactant side, not the product side, but I need 2 of them. And so I'm going to double reaction number 1. I'm going to rewrite it doubled. I'm going to leave off all the states once I've looked around and made sure that all the states are the same, all the waters have the same state, etc. But I'm going to leave it off just so that I don't have to keep rewriting it. And I am rewriting that reaction doubled. I doubled everything. Now, what does that do to the K? When I double a reaction, the equilibrium constant is squared. This is different than how a delta H behaves. A delta H, if you double a reaction, you're going to double the delta H. For the equilibrium constant, if you double a reaction, the new equilibrium constant is squared. That's in the lecture material, if you need to go back and review that. All right, so that is my CH4 matched. Now I just keep going down, matching other things. So let's match the C2H4. As I look down in the reactions, I find it there in reaction number 2. It is on the wrong side. I need it in the product side. I see it in the reactant side. And so I'm going to have to take reaction number 2 and reverse it. Now, I only have one. I only need one, so I don't need to multiply by anything. But I do need to reverse reaction number 2. So I'm going to rewrite it reversed. That means I have 2CO plus 2H2O is in equilibrium with C2H4 and 2O2. So I just took that reaction and reversed it. What does that do to the equilibrium constant? I now have 1 over that equilibrium constant, which is actually the same thing as that equilibrium constant raised to the -1 power. That means the same thing algebraically. Again, this is different than what the delta H does. If you reverse a reaction, the new delta H is the negative of the old delta H. That's not the way that equilibrium constants behave, though. When you reverse a reaction, the new equilibrium constant is 1 over the old one. So I've matched my CH4, I've matched my C2H4. The only thing left to match is my H2. And the only reaction left to manipulate is that third reaction, and there's my H2. Once I've manipulated reactions 1 and 2 to match, as long as I've done it correctly, I should not have to go back and change them. So let's look at reaction number 3 with the H2 in it that I have to manipulate to make the H2 match. But don't go too fast, because you may notice I already have an H2 manipulated. In other words, H2 shows up in more than one spot in my given reactions. That means it's harder to match. Not impossible, but harder. So that H2 is already in reaction number 1, which is written correctly because I matched the CH4, but I've got 6 H2s on the product side. What I'm trying to get is 2 H2s on the product side. I've already got 6. I have 6, but I only need 2 H2s. All right? That means I'm going to have to use reaction number 3 to cancel the H2s in the product side that I don't need. I don't need to reverse reaction number 3 to put more of the H2s in the product side because I already have H2 in the product side. This is more difficult to match. It's like a puzzle you're trying to fit together, but that's how it fits together. I've already got H2s in the product. I've got more than I need. I'm going to use reaction number 3 to cancel the ones that I don't need. How many do I need to cancel? I need to cancel 4. Oops. H2s. I need to cancel 4. So I'm going to need 4 H2s over here on the left to cancel 4 of the H2s on the right to leave me with 2. Well, how do I get 4 H2s on the left? I need to double reaction number 3. If I double reaction number 3, that gives me 4 H2s on the left. I will also have 2 O2s on the left and 4 H2Os on the right. Now, if I did this correctly, I should be able to add these 3 manipulated reactions together to get the desired reaction. And everything that I don't need from reactions 1, 2, and 3 should cancel. So this is a good way to tell. I did cancel 4 of them, leaving me with 2 H2s over here on the right. I did that on purpose, but let's look at the other things that cancel. You'll notice on the left, I have 4 H2Os together, all together, and I have 4 H2Os on the right. So all my H2Os cancel, and it's a good thing they cancel because I don't need them in my final reaction. I also see 2 O2s here on the left and 2 O2s on the right, and they cancel. And lastly, I see 2 COs on the left and 2 COs on the right that they cancel. So once I've canceled everything that cancels, the only thing left is I have, oops, there it is. I have 2 CH4s on the left. Everything else on the left canceled. I have a C2H4 on the right. And I have my 2 H2s left over. So I have manipulated reactions 1, 2, and 3 correctly because I did get the desired reaction. And I forgot to finish up what happens to equilibrium constant K3 when I doubled that reaction. It becomes squared. All that is left is to say my new equilibrium constant for this reaction is going to be the 3 manipulated equilibrium constants multiplied by each other. Back in Hess's law, we added up the delta H's from the manipulated reactions. Equilibrium constants behave differently. We multiply them. So that's going to be K1 squared times K2 to the minus 1, or I could write that as 1 over K2, times K3 squared. You should plug this in. Let's put our numbers in. Let me scroll a little bit. My new equilibrium constant is K1 is 1.2 times 10 to the minus 8, and that's squared. I'm looking up at the problem. I'm going to divide by K2. I'm just going to write it down here. There's a couple different ways I can do this algebraically. And then I have K3 squared, so 1.1 times 10 to the 21, and that is squared. And plug that in. Be careful plugging it in. You should practice plugging this in and make sure you can get all your squares and divided bys. Make sure you're using scientific notation to do this. There is a scientific notation video if you need to go back to Chem 1 and help. I have 1.584 times 10 to the 24. It looks like 1.6 times 10 to the 24 is my answer if I round that.